Today we're going to discuss about the first law of thermodynamics. So this is going to be a brief video. I'm going to introduce you to the equation and then we're going to see the application of the first law of thermodynamics in some cases, for instance in a cyclic process and also in an isolated system. Then in the next video we're going to see a few more applications of the first law. For instance, we're going to use it in an isovolumetric process, in isothermal process, and isobaric process. So this is the equation of the first law of thermodynamics. So delta E with a subscript I and T is the change in the internal energy, and Q is the heat, and W is the work. And in this form I've written that work is in terms that the work that's done on the gas. If it was work that's done by the gas, we would have had a minus sign here. But for now we're going to use it as work done on the gas. Now in some textbooks you might see the first law written in a different way. For instance, like this. Here we also have, actually I should mention that the first law of thermodynamics is actually a special case of the law of conservation of energy. And as we can see here, delta E INT is the change in internal energy, delta EK is the change in the kinetic energy of the system, delta EP is the change in the potential energy of the system. Then we have work plus heat, plus now here T stands for transfer, in terms of transfer of energy. So the subscript MW stands for actually molecular work or mechanical waves, energy that's transferred through mechanical waves. Then T with subscript MT, MT stands for matter transferred. So basically convection. T subscript ET is for electromagnetic, it's for electrical transmission, so basically electrical work. Then ER stands for electromagnetic radiation. Now in this form, the way that I've written it, since the system is, we can say, stationary, because we're not looking for a change in the kinetic energy or the potential energy of the system as a whole. I mean with respect to its center of mass, so we can neglect this. Then in this case that I've written here, there is no matter transfer, so basically since none of the molecules are exiting the system, so we can erase that. Now for the heat here, we can, under the sign, we can actually implement, we can implement electromagnetic radiation. So basically here, instead of writing transfer of energy in terms of electromagnetic radiation, this is included in the Q here. And for work, I'm including in this equation the transfer of energy by mechanical waves and also the electrical transmission. Okay, so now let's move on something else. Let's see the first law of thermodynamics in action in an isolated system. So for instance, let's have a piston and a cylinder. So basically our classic example. So this is the cylinder and here I have a piston. Now this is an isolated system, meaning that we do not have any energy transfer in or out of the system. So what would that mean for our equation? Now the equation was the change in internal energy is equal to the heat plus the work done on the gas. Now, since this is an isolated system, basically we do not have any energy transfer. So basically the heat is equal to 0, which is equal to also the work on the gas, which is also equal to 0. And since these two quantities are 0, also the change in internal energy is 0. Now here we're talking about change in internal energy, because internal energy is basically a state variable that can be such as pressure, volume, and temperature. But here we're talking about change in internal energy. So basically, as we will see later on, as a measure of the internal energy of a system, we have temperature. But we will see later on, as we will dive in more into kinetic theory of gases. Now, what about a cyclic process? Now, we've seen in the previous video that basically the work of a system is, if we take the integral or the negative integral of P times dV, going from V initial, so from initial volume to final volume. So basically that will be the area under this PV, I should say curve, or under this PV graph. Now in a cyclic process, what do we have? If I draw a PV diagram here, so this is pressure, this is volume, and we have a cyclic process, and that will look something like this. Now a cyclic process means that basically the system ends at the same point as the process has begun. So what can we say about, let's say, the change in internal energy? Well, let's say this is point 1 and this is point 2. And the system is going in this direction. Now, since the initial and final points are the same, basically the change in internal energy will be equal to 0, since we're going back to the same position here. So basically we do not have any change in temperature. Now for the heat and work of this process, now as we saw with the integral equation, the first process, or the first part of this graph is from 1 to 2. So basically if we integrate that, it will be this area under here. Then if we go from 2 to 1, then we have this area, this whole area. And basically the work done will be only the area in the circle here. So since the change in internal energy is 0, then what we can say for the work and heat is that basically heat plus work done on the gas is equal to 0. So that means if I take the work done on the gas to the other side, I'll get a negative, and a negative means, what does it mean? A negative sign on work on the so basically heat is equal to minus work on the gas. So basically, since we have a minus of the work done on the gas, that's the same as positive work that's done by the gas. So basically, heat that's entering the system, or all the heat that's entering the system, is used by the gas to do work. And that's it for today.